Welcome everyone in this video lecture series of data structure. In today's lecture, we will discuss the concept of sorting. So initially, I will explain what is the formal definition of sorting and why sorting is required. And after that, we will discuss the most inefficient sorting algorithm, that is the bubble sort. So I think all of you familiar with the term sorting, right? So sorting means arranging a linear sequence of data in a particular order. It could be ascending or descending. So why sorting is required? Because if we sort a particular set of data, then it is very easy to extract insights from the data. Okay, so it enhances the efficiency of the data extraction. So you have already learned the concept of binary search, right? So there was one precondition that data should be sorted either in ascending or in descending order. So that means if my data is sorted, in that case, I can apply one search algorithm that can perform the searching in log n time. But if my data is not sorted, in that case, we have to apply linear search and it will take time complexity of log n. Fine. So one example of sorting is shown here. Let's say we have some data regarding the user base for different social media platform. So if we sort this data, we can easily identify which uh, platform are the market leaders, right? So initially we will uh, discuss regarding the types of sorting algorithms. So multiple classification is possible, but uh, one most popular classification is based on the comparison. Okay, so if element-wise comparison is required, then we classify those sorting algorithms as a comparison-based sorting algorithm. So in this class, we have bubble sort, insertion sort, selection sort, merge sort, quick sort, heap sort. Okay, so element-wise comparison is required in this class of algorithm. There exists another class where directly element-wise comparison is not required. So this kind of algorithm are used in a specific scenario. Let's say we have a data set which contain data from 0 to 100. In such scenario, instead of performing direct sorting, what we could do, we can create one array of size 101. So index starts from 0 and ends at 100. So after that, we can read the entire set of data. Based on the current element, what we could do, we can increase the count for that index. So in this way, we will have another auxiliary array where we will have number of elements for different index. From this information, we can create the actual sorted array. So in this class of sorting algorithm, no direct element-wise comparison is required. So this is called non-comparison based sorting algorithm. So now we will discuss some characteristics of sorting algorithm. These are very important because based on this criteria, we can uh, make some comparison among the sorting algorithms, and we can say in which scenario which is applicable or which can provide better result. So first one is the in-place sorting algorithm. So name is self-explanatory. In-place means no auxiliary linear storage is required. Okay, so that means if I have the data within an array, within the same array, it will perform the sorting. One example is bubble sort. So non-in-place sorting, merge sort. We will discuss these algorithms later in details, but for the time being, you can know their name also. But the concept is very important. What is the meaning of in-place sorting? So that means we are performing the sorting on the same storage. No auxiliary storage is required. Internal sorting. So that means whenever we want to run any sorting algorithm, what will happen? The actual process will be performed by the CPU. So CPU takes the data from my primary storage. But if I have very large amount of data, in that case, we may want to store those data in the secondary storage. But if my sorting algorithm is follow the internal sorting strategy, I have to fetch the entire data from the secondary storage to primary storage. If it is not possible to store the entire data in my primary storage. Primary storage means the RAM, right? So if it is not possible to store the entire data within my RAM, then it is not possible to apply internal sorting algorithms on those data. In case of external sorting algorithms, our data can partially present in my secondary storage and partially present in my primary storage. So some operation will be done in the primary storage, then I can swap out that data and fetch the another set of data. So the concept of merge sort is implemented based on this external sorting principle. So this is useful for large set of data. Stable sorting. So let's say in my data set, there exist multiple identical elements. So if the sorting algorithms preserve the relative order of those identical elements, then we can say that algorithm is a stable sorting algorithm. Now you may ask that, let's say in my array there exists two 7. So what's the matter if I store the second 7 prior to the first one? But this may not be the case for every situation. Most of the time, we work with complicated data. Let's say there exists a data for multiple students, okay, and a particular field is used for the sorting purpose. So now, depending on the situation, we may want to store the first record first and the next one after the first record. So in such scenario, we can use the stable sorting algorithm. To understand this thing in a better way, I want to provide one example. Let's say we are organized one online exam. Okay. Now in that exam, we store the student records along with their marks and their submission time. Now it may happen that multiple students score the same marks, but which student will should get better score? The student who submit the answer first. So that information is present within the same structure in the timestamp field, right? So if I use one stable sorting algorithm, then what will happen? The student entry which appears first will remain before the later entries, though their score are same. So in case of insertion sort, we get this stability. But for selection sort, we will not get this kind of stability within our algorithm. Another very important point is adaptive nature of the sorting algorithm. So adaptive means if the pre-arrangement of the data affects the performance of the algorithm, then we say the algorithm is adaptive in nature. So let's say we provide one almost sorted data. So let's say we have 8 data, okay, where first element is 8 and then 1, 2, 3, 4, 5, 6 up to 7. So this data is almost sorted, right? So only one element is not in its correct position. So in such scenario, adaptive algorithm should take less time. So that means pre-arrangement of the data affect the performance of the algorithm. So insertion sort is an adaptive algorithm. Okay. So that means if we provide almost sorted data, then adaptive algorithm will take less time to perform the sorting. So now we will discuss the worst sorting algorithm or most inefficient sorting algorithm. Now you may ask why we should learn any worse algorithm? Because if you learn this algorithm properly, then you can easily identify what are the loopholes of this algorithm and where we can make optimization. So this algorithm basically place the smallest or highest element in the last position. So this smallest or highest element is just passes as a bubble. Okay, so that's why this bubble sort name is given to this algorithm sorting strategy. So why I am mentioning largest or smallest together? Because it depends na, in which order we want to perform the sorting. So if we want to sort the data in ascending order, in that case, large element will rise in the end of the data. In case of descending order sorting, we have to place the smallest element at the end. So that's why both things are mentioned. So the strategy of the bubble sort is very simple. What you have to do, we have to traverse within the data from left to right. Okay. So I'm considering that we want to sort the data in ascending order. So if we get any two consecutive elements are in out of the order, we will swap them. Okay. So this strategy will ensure that if we complete this thing for one iteration, it will place the highest number in the last position. And that should be the final position for this element. So if we repeat these steps again and again, what will happen in the next iteration? It will place the second highest number in the second last position. In the third iteration, it will place the third highest number in the third last position. So if we repeat this process, eventually we will get one sorted array. Fine. So here you can visualize the how this algorithm works. So we have 10 elements, 10 data, 1 to 10, but they are not in proper order. So when we will perform bubble sort, what will happen? In each iteration, it will place the highest number in the last position. So the green bars represent the actual position of these elements. Clear? So I want to repeat this thing again. So in the first iteration, it will place highest number in the last position. That is my 10. In the next iteration, it will place 9 in the second last position. Then we will have 8. So the red elements represent the consecutive elements, okay, on which we want to perform the comparison. So this is fourth iteration. So we place 4, then 3, 2, 1. So all are now become green. So that means sorting is done. So visually you can identify that we have able to sort this array. Okay. So this code, this visualization is also created using one program written in Python because we want this kind of visualization. And basically within the code, I have write the algorithm of bubble sort. And we store different state of my list, and then I create this visualization. So you get some idea, right? How bubble sort algorithm works. So now I want to introduce this bubble sort algorithm, but first of all, I want to write the unoptimized version of this algorithm. So you already know how to write one algorithm. First, you should specify the name, then its input and output. So name is bubble sort. Input should be one list of integers. Okay. Let's say n elements are there and the list name is A. And it is not sorted. Okay. So this is one unsorted list. And output, we are using bubble sort. That means sorting will be done within the same array. So within the same list, we will get one arrangement of the existing element, and that arrangement will be ascending order sorting of those elements. Fine. So now we have to specify the steps by which we will transform this input to its corresponding output. So basically, we will receive the list A and N within our algorithm. Then what we will do, we will repeat one loop. So how many times we will repeat? 0 to n minus 1. So total number of iteration will be n, because in the first iteration, we are placing the highest element in the last position. In the second iteration, we are placing the second highest element in my list. Okay. In the second last position, right? In the third iteration, we are placing third highest element in the third last position. So how many elements present in my list? So there are n elements, so n number of iteration is required. So that's why it starts from 0 and ends at n minus 1. Probably some of you identify that we can optimize this thing. I will address that thing later. But For the time being, we are discussing only the unoptimized version. Okay. Now, within one iteration, what we will do? We will perform element-wise comparison. So how many elements are there? N. So what are the valid index? 0 to n minus 1. So my for loop will run from 0 to n minus 2 because I want to swap between aj with aj plus 1. So that means if I ends my loop in n minus 2, so that with the help of j plus 1, I can reach to the last index. Okay. Now, how to denote the consecutive element? So current element is pointed by j. So the next element will be pointed by j plus 1. I want to sort this data in ascending order. So aj must less than equals to aj plus 1. If I get any contradiction, we will swap them. So ultimately, we will get sorted representation of A. Clear? But some optimization is possible within this algorithm. First of all, you can identify here that if we able to place n minus 1 element in its correct position, that means nth element is also in its correct position. Okay, so think about the previous visualization. We have already placed 9 elements in its correct position. Okay, so that means the 10th element, that is my 1, also in its correct position. No swapping is required for that. So we can shrink its limit from n minus 1 to n minus 2. So that means my loop, external loop will run for n minus 1 time instead of n times. Okay. Another thing, in my previous visualization, you can observe that whenever we place a particular element in its correct position, we mark it with green color. So that means that is the appropriate position for that element. So no further swapping is required, or no further comparison is also required for that element. Okay. So that means in case of first iteration, we should reach up to index n minus 2. But in the next iteration, is it required to compare the element present in my n minus 1th index? No. So in that case, we can reach up to n minus 3. Next time, we can reach up to n minus 4. So basically, we can shrink the limit of inner for loop. So these two optimization is possible within my algorithm. So that is shown in the optimized version of this sorting algorithm. So here, my ith loop will run from 0 to n minus 2. And what about my jth loop? So jth loop will run from 0 to n minus 2 minus I. So initially value of I is 0, so that means it will run up to n minus 2, but next time I will become 1, so I will shrink the limit of this inner for loop. Okay. So here we optimize the loop count in my algorithm. Another optimization is possible. Let's say we provide one partially sorted array. Let's say the numbers are 8, then we have 1, 2, 3, 4, 5, 6, 7. So in the first iteration, what will happen? It will place 8 in its correct position. So obviously we will get the sorted sequence. So no further swapping will happen. So that means after the first iteration, no change will happen in my array. Okay. So rest of the iterations are useless. So we can remove this kind of unoptimized behavior of my algorithm. So basically, we can keep track whether swapping is happen or not in a particular iteration of the outer for loop. If no swapping happened, then what we can do? We can terminate the outer for loop. So in that case, what will happen? It will return the result directly. So in this way, we can reduce number of iteration within my algorithm. So these two optimization is possible in my bubble sort algorithm. So this is the most optimized version of the bubble sort algorithm. So here you can see that prior to enter in the inner for loop, we will set a flag variable to false. So whenever we will perform any swapping, we will set it to true. So after the inner for loop, we will check whether the state of this variable is false or true. If it is false, that means no swapping happened. So we can easily terminate the outer for loop. So eventually it will terminate the entire or it will uh, terminate the entire algorithm. Okay, clear? So now we will discuss the time complexity analysis. So if I want to talk about time complexity, at first we should decide which kind of case we are considering. There exists best case scenario and also the worst case scenario, or we can consider the average case time complexity for the for this kind of analysis. So when we will have the best case scenario, let's say we want to sort the data in ascending order and we already provide one array having data in ascending order. So if we use the optimized version of the algorithm, what will happen? It will reach all the elements from index 0 to n minus 1, and it will identify that no swapping happened. So in that case, it will terminate the algorithm. So in that case, time complexity will become order of n. But if my algorithm is not optimized, then it will remain order of n square. So from this point, you can identify why optimization is required, right? But what should be the worst case time complexity? So basically, we have two for loops in a nested structure. So if my outer for loop runs n time and inner for loop runs n time, then the code present within my inner for loop will run for n square number of time. But the case is not similar to that, right? Because we are syncing the limit for my inner for loop. So basically, worst case scenario will happen if we have the data in reversely sorted. So how many times our outer for loop will run? It will run for n minus 1 time. So in the first iteration, we will visit all the n elements, right? Our inner for loop generate index from 0 to n minus 2, but with the help of k plus 1, we are reaching to the index n minus 1 also. So that means we are visiting all the index from 0 to n minus 1. That means we are visiting all the n elements. So first iteration, we will visit all n elements. In the next iteration, we will visit only n minus 1 element. Then we will visit n minus 2 elements. So eventually, it will get decreased. So this is a monotonically decreasing value. So eventually, we will reach to 1 in the n minus 1th iteration, right? So the cost polynomial can be represented like this: n minus 1 plus n minus 2 plus n minus 3 plus dot 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 up to 3 plus 2 plus 1. So we know the summation of n natural number is n into n plus 1 by 2. But here we have n minus 1 in the last term. So basically it will become n into n minus 1 by 2. So this polynomial is nothing but a degree 2 polynomial. So that means this algorithm belongs to the class of order of n square. In the average case, we can consider that to compute the average case, you can do one thing: you can count the number of swapping. Okay, so you can say in the first iteration it will perform n by 2 number of swapping. Next time n minus 1 by 2. In this way, you will get another series, but ultimately you will get one polynomial with degree 2. That means in the average case, we also have the time complexity of order of n square. Fine. So now if you in the lab, you should implement this algorithm. So these are the prescribed function signature. So there should be one create array function by which you can create the array dynamically. In this function, you will pass address of the integer pointer as well as the size. For my scan array, we have to pass the array along with its size. Similarly, we can write another function to print the array. And this should be the signature for my bubble sort. In this function, we will pass the starting address of the array, its size, and one Boolean flag variable. This is for uh, testing purpose. Okay, basically, if we pass the flag value true, then what I want to do? I want to print the state of the array in each iteration. So each iteration means I am talking about the iteration of the outer for loop, so that I can identify that in each iteration I am placing the highest element in the last valid position. Okay, and if this flag is true, it's supposed to print how many number of swapping it has performed. Okay, so basically, if you want to perform the analysis of this bubble sort algorithm, you should have this information. If you want to discard this information, then what you have to do? You have to pass false value within this function. Is it clear? So I hope you can implement this code in the lab. Thank you.